Hello everyone, my name is Brad Elkins. I'm the Director of Technical Sales at EOS Remediation. And today I want to talk to you about biotic, abiotic, or both for enhanced reductive dechlorination. For those of you who are not familiar with EOS Remediation, we're a remediation product vendor. We're most notably responsible for the development and formulation of several cornerstone technologies, including emulsified vegetable oil, or EOS, for the treatment of chlorinated compounds, nitrates, perchlorate, hexavalent chromium, and a variety of other recalcitrant compounds. Electron acceptors, that's our EAS and EOX product for the treatment of petroleum hydrocarbons. Zero valent iron, which will be discussed today for abiotic degradation. pH buffers for aquifer pH adjustment and metals immobilization. Bioaugmentation cultures, that's the bacterial cultures for treatment of chlorinated solvents, chloroform, 1,4-dioxane, and petroleum. We're always pushing the envelope on research and development, especially in the area of emerging contaminants. And we're constantly looking for ways to improve upon our existing products and technologies. We've been in operation since 2002. We're headquartered in Research Triangle Park, North Carolina. And in Europe, we're represented by QM Environmental. Robert Wagenveld, the managing director, his contact information is on the side there, and he would be your direct point of contact for all projects inside of Europe. We have 6 distribution points strategically located around the world, including in the Netherlands, so any of our projects that occur inside the European Union can be locally sourced. Our leadership is President Ann Borden and her husband, Principal Engineer Dr. Robert Borden. Dr. Borden is also Professor Emeritus at North Carolina State University. So now I'd like to do an introduction to enhanced reductive dechlorination. For this to occur, you need an electron donor and an electron acceptor. For remediation, the electron donor would be the emulsified oil substrate, or the EOS. The electron acceptor would be the contaminant, or the PCE in this case. The EOS, or the EVO, is fermented into hydrogen. And there are a group of microbial organisms that are responsible for taking that hydrogen and through microbial respiration, exchanging a chlorine with a hydrogen and thus degrading the contaminant. This would continue in a sequential manner, removing a chlorine and replacing it with a hydrogen until you get complete ERD, or enhanced reductive dechlorination, ending in ethene, which is a non-toxic end product. Now, this last step to do the complete conversion to ethene is a pH sensitive process and requires a neutral pH for the microorganisms to thrive. And we can provide a proprietary pH adjustment product, CoBuff MG, to facilitate that. So just a little bit of microbiology. There are more microbes in a teaspoon of healthy soil than there are humans on Earth. And as of 2018, there is an estimated 1 billion species of bacteria. Now, we're only concerned in one group, the D-halorespiring bacteria. And specifically within that group, we're most concerned about D. halococoides. That's the organism responsible for the complete conversion of chlorinated solvents to ethene. So he takes that last critical step of converting vinyl chloride into ethene. And he needs hydrogen in order to do that. So now I'd like to explain how we can provide hydrogen to D. halococoides. So soybean oil, which is the primary component of EOS, is a triglyceride. It's got a glycerol molecule with 3 long-chain fatty acids attached to it. Upon injection into the subsurface, it goes through fermentation and it produces hydrogen and fatty acids. Now, for most in-situ bioprojects, people use TOC, or total organic carbon, as a metric for performance. And you can use that with EVO, but you just need to know a few things. Initially, that initial burst of TOC that you see, and this is shown here on the right-hand side in that TOC graph, that initial burst of TOC is most likely glycerol from the initial reactions of the soybean oil in the subsurface. And then TOC concentrations drop off with time. This is totally normal. And most of the time what we end up seeing through a groundwater TOC analysis is not the oil itself, because the oil is insoluble. What we're actually measuring are the fatty acids that have been produced from fermentation. In this case, we're showing it as acetate. Now, we can utilize both hydrogen and acetate for the degradation of PCE to DCE. And there are a variety of microorganisms that can do this, not just D. halicoides. But to go from vinyl chloride to ethene, we need hydrogen and we need D. halicoides. And hydrogen is utilized very rapidly in the subsurface. It's used for a variety of other processes, not just dechlorination. So we must bring the oil into direct contact with where we want treatment. And then where can we produce hydrogen? Well, as I mentioned, you can produce it from the soybean oil itself. You can also produce hydrogen from some of those volatile fatty acid fractions that are produced during fermentation. But you cannot produce hydrogen from acetate. Once the soybean oil ferments into acetate, it can no longer be further broken down into hydrogen. Now, this hydrogen production is important for complete dechlorination, and we can see that in data from this site. So here I'm showing a injection well from an actual remediation site. It's highlighted in green here. And at this well, they got complete dechlorination to occur. And you can see that they had a lot of different volatile fatty acids, not just acetate, but they had propionic, butyric, and others. And because of that, they were able to form hydrogen from those other fatty acids. Now, this goes hand in hand with emulsion transport. If we can get the emulsion to transport through the aquifer, then the chances that we make contact are going to be increased. And so how we can do that is making an emulsion that has a very small droplet size. So for our EOS Pro product, the oil droplet size is about 1 micron. And that can easily pass through most pore spaces in most aquifer settings. And you can see that here depicted in the upper right-hand corner. This is a microscope slide, and we're seeing little oil droplets as an emulsion cluster passing through the pore space. So if we had good transport, we would see a distribution of fatty acids like what we see in the graph to the left-hand side in green. Conversely, if we don't have good transport from that same remediation site, they were monitoring their volatile fatty acids 10 feet down gradient. So the graph highlighted in red shows what you would consider to be poor oil distribution. They had acetate or acetic acid because that is a somewhat mobile fraction and was able to move 10 feet down gradient. And they did get degradation. They got TCE to convert to DCE, but they did not form any ethene. So they did not have complete reductive dechlorination at this well. So this would be a case where maybe you don't have good oil distribution. And you can see in the image on the bottom right, this is emulsion that has now flocculated and can no longer pass through the pore space of the aquifer. And therefore you wouldn't get transport, and therefore you wouldn't get good degradation. Now, beyond the characteristics of the emulsion, you also need to consider how much water you're injecting. So here we're looking at a graph of pore volumes injected versus contact efficiency. And if we look first at the blue line, we're injecting all of our wells simultaneously. And if we inject about 50% of the pore volume, you can see that we're achieving a little over 70% contact efficiency. Now, if we inject our wells simultaneously, there's a good chance that we're going to create stagnation zones in between each of the wells. There's going to be kind of this repulsion effect between the two wells based on flow. And so there's going to be a part of the aquifer that's going to go untreated. So to increase our contact efficiency and eliminate those stagnation zones, we recommend alternating your injection wells so that you inject every other well, leaving a space in between or a injection well in between. And you can see when we do that, that's depicted by the pink line on the graph, that you basically get about a 10% increase at the same pore volume dosing or injection by alternating your wells. So instead of getting 70% contact efficiency, by alternating, you're getting over 80% contact efficiency. Now we know if we follow all of these guidelines, if we have a small oil droplet size or just a good emulsion in general, we're injecting enough water, and we're spacing our wells appropriately, this technology is going to work. And we can see that here when we compare enhanced bioremediation to, say, chemical oxidation. Now, chemical oxidation works. You can see that the graph above, they're getting very dramatic results initially upon injection, but almost all of those sites ultimately end up with rebound. When we look at enhanced bioremediation, each one of these lines is an individual site. And you can see that the overall trend for all of those sites is that they are decreasing. Now, it's not as dramatic as the ISCO, but the overall success of the projects are much higher. But there are some limitations to bioremediation. So your site conditions matter. To get good biodegradation, you must make sure that your concentrations aren't too high. So what we can see here in both these data sets for both TCE and TCA is that there is kind of an upper limit for degradation efficiency with concentration. So for TCE, if our concentration gets above, say, 5 or 6 milligrams per liter, it's not that you don't get degradation. It's just that your efficiency of degradation starts to slow down. And the same thing is true with TCA. When you get TCA above, say, 15 to 20 milligrams per liter, same thing happens. You're still degrading it, but you're degrading it much more slower or less efficient than you would have if the concentration had been lower. Also, if we have mixed plumes, if you have both a commingled TCE and a TCA plume, for example, the TCE inhibits the TCA degradation, and vice versa. The TCA inhibits the TCE degradation. So having commingled plumes can actually kind of work against you in terms of degradation efficiencies. As I mentioned at the beginning, this process is pH sensitive. And to go from PCE to DCE, the range of pH can be basically between about 5.5 and 7. You see that your rates of removal start to decrease when you get below 6. You do get removal and conversion, but it's just going to start happening in a slower pace. Now, for the critical step of converting vinyl chloride to ethene, the graph at the bottom right, you can see when you get pH below 6, your degradation rates really drop off much more dramatically. And by the time you're at pH 5.5, you're basically getting no degradation at all. So maintaining a neutral pH, especially for creating ethene, is critical. Now, where does this acidity come from? Why would our pH drop at a remediation site? Well, one quick and easy answer is that maybe that's just the prevailing condition at the site. I know here in the southeast of the United States, we have some pretty acidic groundwater in certain locations. But also, you can be generating acidity from the remediation effort that you're using. So here I'm showing the amount of hydrogen per kilogram of the substrate, and I've circled here soybean oil in yellow. And you can see that soybean oil produces a lot more hydrogen than some of the other commonly used carbon substrates. And I've noted here zero valent iron. It does also produce a little bit of hydrogen. And that's a little bit of foreshadow to where we're getting ready to go in the presentation. Also, as we're producing this hydrogen, we're also producing some acidity. Now, the reason we use soybean oil for EOS is that we're producing a lot of hydrogen, and we are producing some acidity, but it's much more moderately produced than some of the other substrates by comparison. And you can see that zero valent iron actually consumes acidity, so it's not dependent on pH like some of the organic substrates are. So this brings me to then, well, let's discuss the removal mechanisms for zero valent iron. So for ZVI to degrade chlorinated solvents, the ZVI must actually physically touch the PCE molecule in this case. And when that happens, you're going to remove 2 chlorines at a time, and you're going to oxidize the iron. So you're going to convert PCE to dichloroacetylene. And this process is known as reductive elimination. Now, because we've injected the ZVI into a saturated environment below the water table, while that's going on, ZVI is also coming into contact with water. And when that occurs, there's a reaction. The iron is oxidized, there's a little hydrogen formed, and there's where your alkalinity is formed. Now that hydrogen that's produced can be used biologically for the process we just described, or ZVI can continue to sequentially remove one chlorine at a time, and this is known as hydrogenolysis. Either way, both pathways can ultimately lead to ethene. Here we can see the complete breakdown of PCE to ethene, and we have reductive elimination on the left-hand side and hydrogenolysis on the right-hand side, or just normal biodegradation. Okay. Now it's critical that for the reductive elimination to occur, that the PCE and the ZVI come into direct contact. So this is where your ZVI selection criteria becomes important. You want to make sure that you're appropriately selecting ZVI for the reactivity, the injectability, and the cost and longevity that you're hoping to get out of that substrate. So what we see here at the bottom is a graph that shows ZVI particle size diameter, that's D50 microns, as a function of rate of removal of chlorinated solvents. And you can see that as you get smaller in particle size, you are increasing your surface area, and therefore you are increasing your reactivity. Now there's a trade-off. The larger the ZVI particle, the longer it's going to last in the aquifer. Large scale ZVI, something on the order of, say, millimeters in diameter, that can last for years in the subsurface. And it comes at a much reasonable cost because larger scale ZVI is easier to produce, so it is cheaper. But you don't get the reactivity. And as you decrease particle size, you see that not only are we increasing reactivity, but we are decreasing longevity and we are increasing cost. As you get smaller in particle size, it becomes more difficult to manufacture and therefore it becomes more expensive. Now for aquifer injection, for in-situ remediation, my opinion is that the best range to use for ZVI for injection is going to be between 1 and 10 microns. Now I show here highlighted actually 1 to 50 because there are many, many projects out there where based on the hydrogeology or just your geology in general, or perhaps your injection methodology, you can get away with injecting a little bit larger particle, something up to about 50 microns. So that's why I'm including that. But I think for best transport, for best distribution, you're going to get the best results by utilizing a zero valent iron with a particle size between 1 and 10 microns. Anything smaller than 1 micron, which would be considered nanoscale, it's going to be extremely expensive. It's not going to last very long. And actually, as you get smaller in diameter, you actually end up flocculating those particles. And so they actually don't inject as well as you might think. So how would we consider marrying these two technologies? What's the differentiation here? And how can we determine when best to utilize both technologies or when we might think about combining them? So here I'm showing a database that was put together by Travis McGuire at GSI Environmental. And I want to start on the left-hand side with the bioremediation graph. So the graph there shown with the little plots in green. Each one of those green dots is a site where we are measuring the concentration of chlorinated solvents before treatment and after treatment. And then the dashed lines that are running diagonal on the graph, those are orders of magnitude reduction. Okay, so if we break this graph down, you can see first that I've circled in black a group of sites that basically had a poor response. And that could largely be attributed to the dependency of the site conditions. So all the things that I just discussed, the high concentration, commingled plumes, maybe pH was too acidic. There's a variety of other factors. But generally speaking, for this analysis, we're going to say that, well, this technology is pretty site dependent. And you can see that in this data. Now, also what you'll notice, highlighted in green below in the little green circle, you can see that a lot of these sites were able to achieve results below MCL, MCL being that blue dotted line there. So there, if you utilize bioremediation, there's a really high chance that you're going to achieve your remediation goals and get past very stringent cleanup standards. If we look at zero valent iron now, this is the graph on the right-hand side. Again, it's the same thing as the bioremediation plot, just we're looking at zero valent iron now. Basically, the same analysis is in reverse, or the inverse. So we are seeing in the purple circle there, we are seeing that the success rate is a little bit better. There are not as many poor responses from the technology. So you kind of get better overall reduction. But if you look, the black circle there, none of the sites that were shown in this data set got below MCL. So there's kind of a lower chance that you're going to achieve strict cleanup goals with ZVI, and that's mainly attributed to the fact that the technology is incredibly contact dependent. So where I think a sweet spot is this section highlighted in yellow. Basically, when you have chlorinated solvent concentrations between 1 and 10 milligrams per liter is when you might think about using one or the other, or maybe consider combining them together. I think that anything over 10 milligrams per liter for bioremediation, you might be a little bit limited in treatment, and that's where ZVI could step in and kind of help knock down concentrations initially, and then you could come in with bioremediation and polish it off. Now, you've got to also think about costs. So bioremediation in general is going to be cheaper than using zero valent iron. But depending on your site conditions and your cleanup standards, that might help you further narrow it down. So the sweet spot for the technologies is you would use EOS for ERD when you have low to moderate contaminant concentrations, something less than 10 milligrams per liter as example. You would have a single contamination group, and your pH would be neutral. Now, low acidity or low pH can be managed through a buffer like CoBuff. But if you have other site conditions, that's when you might consider using zero valent iron for ERD. So if you're dealing with DNAPL or really high concentration, something over 25 milligrams per liter as example, if you're dealing with mixed contaminant plumes, again, if you have that concern about pH, but you just got to remember that ZVI is incredibly contact dependent. So contact is key for good degradation. So you might consider using zero valent iron on smaller hotspot areas and then utilize that as a jump start for bioremediation. Both of these technologies utilize the same redox conditions, meaning that both of these technologies are used in anaerobic conditions where your ORP is way negative. They both produce hydrogen, so there's a kickback there for ZVI for biodegradation. And there's no cross interaction, meaning that there is no other secondary reaction that occurs between the EOS and the ZVI. So they're very safe to utilize in combination at a site. So if you're considering combining zero valent iron and EVO, then you might consider creating in the field a product we call EOS ZVI. So you would utilize any microscale zero valent iron that you would like to use. You can contact QM Environmental to get a source of zero valent iron. And then you would mix that in the field with EOS, either EOS Pro or EOS 100. I would recommend that you combine ZVI with EOS 100. And the reason for that is that EOS 100 is a waterless oil product. So it comes to you with no water added, and you would mix the ZVI with the EOS 100 in the field, thereby not losing any reducing power upon that initial mixing step. Once it's created, then you could dilute it with water and inject it. So you could wait and save all that zero valent iron reducing potential until the moment you're actually ready to prepare it and inject it into the aquifer. Now below I have a recommended preparation for this field EOS ZVI. This is by no means set in stone. This could be adjusted depending on your mixing capabilities or maybe your site criteria. This is a good place to start. But once you combine all these ingredients in the field, you would then dilute it with water, and then you would inject that material. And ideally, if it was all mixed appropriately, it would look something like this image to the right-hand side. This would be prepared EOCVI with a microscale ZVI, and you can see how easily that it disperses within water. So very nice, easily injectable material there. Of course, that is dependent on your capability to mix in the field and the type of iron that you ultimately end up using. But QM Environmental and myself here at EOS Remediation, we're here to help you make this process work to the best of your ability in the field. So if this is something that's of interest to you, please engage us. We're happy to help you out. So this concludes my presentation. I hope you enjoyed. If you have any questions at all, please feel free to reach out to Robert Wagenveld over at QM Environmental, or you can reach out to myself, Brad Elkins, and our contact informations are up there on the screen. Thank you again so much for watching. Have an excellent day.